You used to call me on my. You used to. Yeah.
Math morning or math afternoon, math night. I'm not sure when you're watching this. Today, as you can see, we'll be talking about real numbers. And as you can see by my Bitmoji collection, I like to keep it real. Let's talk some real numbers. And again, when I write things down, you should pause the video to make sure you copy everything. So the first thing we have is set notation. This is how we describe a set of numbers. It looks like two brackets and it has a little indent in the middle. Mine aren't that pretty. You have better handwriting than me, so you can make them look nicer. We use these to show a group of numbers. So within a set, you might have -5, 22, and a 100 bracket. So these are a group of numbers or a set, and this is in set notation. The definition, which you can write down, is a set of the numbers. And no, that's not a set of hashtags. That is the number symbol. So now let's talk about real numbers. You might be thinking, Mr. Durkis, aren't all numbers real? Well, no. There are some unreal numbers that you'll learn about later on in higher math. For Algebra 1, most numbers we talk about will be real numbers. And these are groups of numbers, big groups, not like a little set of 3. These are large, some are infinite. So natural numbers, this was one of the first big math ideas. Somebody started counting. All right, let's say they were counting sheep. One person had 1 sheep, another person had 2 sheep, another had 3, blah, blah, blah. When I say blah, 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 that means it goes on to infinity. So these are numbers that you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way until you will go forever. The next big idea in math someone thought of was the number 0. So imagine someone thought, oh, 0, I invented that. What a wonderful idea. So this set of numbers, whole numbers, includes 0. So it starts with 0, 1, 2, 3, blah, blah, blah. It goes on forever. So whole numbers, they are very similar to natural numbers, but the only difference is that whole numbers include 0. Another big math invention, a big math idea, was when someone owed somebody something. So let's say Steve owed Bobby 5 sheep, so he would have -5. So integers include negative numbers, and let me start with -3, and this actually goes forever in the negative direction. Then -2, -1, 0, 1, 2, 3, blah, 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 into infinity. So those are integers. They include negative numbers. They also include all the whole numbers and natural numbers. The next ones are rational numbers. Any rational number can be expressed as a fraction. So at some point, someone probably had, 4.5 sheep. Maybe they ate half of it, and they needed to express that. So these are normally fractions, but they could be any number expressed as a fraction. Like 1/2, that's a fraction. Also, 4/1, this is a fraction, but that's the same as 4. So 4/1, 1/2, those are all rational numbers. The next one, irrational numbers. If rational numbers are fractions, irrational numbers cannot be expressed as fractions. Let me write this down. Can't be expressed as fractions. One example of this that you might know is pi. It goes 3.14, blah, 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 blah. It goes on forever, and it cannot be expressed as a fraction. If I was going to draw a Venn diagram of this, right, I would start with the natural numbers. And then whole numbers, they include all the natural numbers and 0. So if I drew a bigger circle, these would be whole numbers. Integers, these include all of the whole numbers and negative numbers. So I'll draw an even bigger circle for integers. After that are rational numbers. Every integer can be expressed as a rational number. So everything over here can be a rational number. Then irrational numbers, these can't be expressed as fractions. So these are going to be all by themselves over here. I'll give that an IR. And then if I put a big box around this whole thing, that includes that, these will be real numbers, and sometimes you see it written as this big fancy R with 2 lines. So those are real numbers. Now let's talk a little bit more about rational and irrational numbers. Rational numbers, those can be expressed as fractions. You see over here we have -1/8 and 16th over 11. Those are both fractions. Let me show you this picture. That's Arnold Schwarzenegger. He is the Terminator. Why do I say or show you this picture of the Terminator? That's because rational numbers can either be repeating or terminating. What do I mean by that? Let me pull up my calculator. Oh, that's the wrong website. So my calculator, -1/8. If I type that in, -1, when it's a fraction, that just means divided. -1 divided by 8, -0.125. This ends, it just stops right there. So that is a terminating fraction. Let me try 16 divided by 11. 16 divided by 11, 1.4545454545. It ends with 2 5s because it rounded, but this is repeating, right? The 4 5s go on forever and ever and ever and ever and ever. Now, irrational numbers, these are not like rational numbers because they cannot be expressed as a fraction. And let me show you this other picture of Arnold. Why do I show you this one? Because it's irrational, right? He's wearing these tube socks. He's wearing all red. He looks like a tomato. I don't know. It's irrational. But the square root of 2, what does that equal? Let me go back to my calculator. Pull it up on this side. Clear it. Square root of 2. 1.4142356237. It does not repeat itself. It goes on forever, just like that. So that is an irrational number. You hear this one a lot over here, pi. If I type that into the calculator, pi, what does that equal? Most of you know is 3.14, but this number goes on forever and ever and ever and ever. So it's irrational. There's no pattern to these numbers going forever. So again, rational numbers are repeating or terminating, and irrational numbers are non-repeating and non-terminating. Rational numbers, you have the terminator. Irrational numbers, this is not the terminator. All right. Now let's look at some numbers and figure out if they're whole numbers, integers, rational, or irrational numbers. The first one, 5, that's a nice one to start with. We know it's a whole number. Remember, whole numbers go from 0, 1, 2, 3, 4, 5, 6, 7, all the way until infinity. If it's a whole number, that means it's also an integer, because integers are all whole numbers but include negative numbers as well. And if it's an integer, that means it can be expressed by a fraction, so it's also a rational number. 5 divided by 1, that is a fraction, and so that makes it a rational number. 0.6. So is that a whole number? No. Is that an integer? No. Is it a rational number? If you remember from the last slide, if it's terminal, if it ends, that means it can be expressed as a fraction. So that is a rational number. And to think of an example, if you did 6 divided by 10, that would equal 0.6. Negative 24, is that a whole number? No, because it's negative. Is it an integer? Why, yes it is, because integers include those negative numbers. And again, if it's an integer, then it must be a rational number. Now we have 9 divided by 7. Is that a whole number? No. Integer? No. Is that a fraction? Yes, it is. So I'll bring that one down here. Now we have the square root of 11. Now I need to find out, does this repeat itself forever, or does it end? So let me go back to my... Oh, wrong thing again. Alright, square root of 11. So I do the square root. Oh, but I get rid of that 9. Square root of 11. 3.3166247903. I don't see any pattern or repeating in there, so that one I can say is going to be an irrational number. Now we have 2.823. Alright, what is this bar on the top of the 2, 3? Well, that means that it repeats forever. So this is really 2.823, 23, 23, 23, 23 forever. So if it is repeating, that means it's going to be a rational number. Lastly, we have 2 2/3. Is that a whole number? No. Is it an integer? No. Is it a rational number? Well, it's a fraction, so a yes. Something that you'll be asked to do is convert mixed numbers into fractions. 2 2/3, that was the last example from the last slide. This is a mixed number. A mixed number is part integer, the 2, and part fraction, the 2/3. Let me just get my pen up. So this right here is a mixed number. These are all mixed numbers. So again, a mixed number has an integer and a fraction. We want to convert these into improper fractions. An improper fraction is just a fraction. There's no integer at the beginning, and the numerator, which is the number on the top, is greater than the denominator, the number on the bottom. You can convert these following these simple steps. You take the denominator, the number on the bottom, and multiply it by the integer. So 3 times 2, that equals 6. It's going to be 6. And then you take your answer and add the numerator. So the next step is addition. That's a plus sign. Let me put plus. 6 plus 2, that's going to equal 8. And then you keep the same denominator. So this right here is an improper fraction. Improper fraction. And this is what mathematicians most likely prefer. The higher you get in math, the more likely you are to see improper fractions instead of mixed numbers. You do see mixed numbers a lot in recipes, but in algebra, calculus, you see a lot more improper fractions. When you have a negative integer, all you have to do is pretend the negative sign is not there at the beginning. You follow the same steps. You multiply, and then you add. Plus, that's a plus sign. So 5 times 3 is 15. 15 plus 4, that's 19. And we keep the same denominator. So 19/5. But we had a negative sign to start with, so we have to make it negative to end with. So when you have a negative number, you just pretend it's not negative, but then at the end, you put the negative back on. Right now, I want you to pause the video and try this one by yourself. Did you get 15/8? If not, rewind the video and watch the directions again. Another thing you're going to need to know is absolute value. That's the distance between a number and 0 on the number line. Let's start over here. We have the absolute value of -8. So if I drew a number line, I have 0 right here, -8 is over there. How far is this 0 from -8? Well, the distance is a positive. We're going 8 in the negative direction, so this is 8. When you have an absolute value, it's always going to be a positive number. Alright, let's look at 9. So this, if I continue the number line, 9 would be somewhere over here. So how far did I go from 0 to 9? Well, I went 9. A common mistake that I see a lot is people, they just change the sign. If it's negative, they make it a positive. Over here, -2 3/4, well, that's going to equal +2 3/4. Sometimes in this one over here, you might have to do a little extra work. If you have an operation inside the absolute value brackets, you need to do that first. 12 minus 7, that's 5. So this is the same as the absolute value of 5, and that equals 5. Lastly, we have negative absolute value of 5/3. If the negative's on the outside of the absolute value, then it's different. It's going to be negative. So the absolute value of 5/3 is 5/3, and then we make that negative. So when the negative's on the outside, your answer will be negative. Perfect. This should be review. You should have learned it before. If not, you need it going forward. Now we're going to put all these numbers in order from least to greatest. Over here we have 3.6, the absolute value of -3.2, 13/4, and 3 3/8. So what I would do, just so we can compare them, is convert them all into decimals. So 3.6, that's already a decimal, so I'll just write that over here. 3.6. The absolute value of -3.2. Well, we know absolute value is the distance from 0. If it's negative on the inside of the bracket, it's going to be positive. So that's really 3.2. 13/4. What we can do, turn this into a decimal. So let me get the calculator up again. Oh, I did it again. Man. Alright, so 13 divided by 4. 13 divided by 4. 3.25. 3.25. Now let's turn this mixed number into an improper fraction first. 8 times 3 is 24, plus 3 is 27. So 27 over 8 is the improper fraction. Let's turn that into a decimal. So now we have, let me clear this, 27 divided by 8, 3.375. 3.375. So let's order these from least to greatest. So which is the smallest? We have 3.6. That looks like that is the largest. They all start with 3, so we need to see what is the next number that's the biggest. So 3.6, that would be the largest. This one starts with 3.2. This one also starts with 3.2. So what's bigger, 3.2 or 3.25? Well, would you rather have $3.20 or $3.25? Right, $3.25 is bigger because the next number here is really 0, and that's a 5, so that is 0.5 more. So the smallest is 3.2, and then we have 3.25, 3.375. Right, 3.3 is bigger than 3.2. All right, so there we go. least to greatest. If I put them on the number line, 3.2, well, there's 3. So 3.2 I'll put right there. 3.25, that's a little bit bigger, so that'll be right there. 3.375, well, that's close too. They're all kind of jumbled up right there. And 3.6 is kind of a little small, but they're all between 3 and 4 squeezed in there. But when you write your answer, you want to keep them in the original form. So 3.2, that's really the absolute value of negative 3.2. So absolute value, negative 3.2. Absolute value. 3.25, that was 13/4. 3.375, that was 3 3/8. And 3.6, that was 3.6. So that's how we do that. Now I want you to pause the video. Pause it. Let me write. Pause. And try to do these. So convert these all to decimals and order them from least to greatest. Great. So let's see. I'm going to convert these all to decimals too. So -1 is -1. -4/3. Let me go to my calculator. Clear that. -4 divided by 3. -1.33333. So when I write that, -1.3, I can just put the bar on the top. -1.2 is just like that. -√7. Let's see. -√7. -2.6457. I'll round it to -2.64, but it won't be a 4, it will be a 5 because this next number is 5 or greater. So -2.65. -2.65. Alright, so when they're negative, the larger the negative number, the more negative it will be. So I think of this also like money. Would you rather owe someone $1 or $2.65? Right? $2.65 seems like more, so the greater number is actually -1. So -2.65 on the number line, there's 0. -1, -2, -2.65, that's like right over there. The next one, we have -1, -1.3 repeating itself, -1.2. Well, owing someone -$1.3, right, that's the second largest amount, so that's more negative. So -1.3, that's like right there. -1.3 repeating. -1.2, that one comes next. And that one's a little bit closer to -1. And lastly, -1 is last, which is right on there, -1. And again, right, put these in the original form. So -√7, that was the first. -1.3 repeating, that was -4/3. -1.2 was next. And then -1. Perfect. So that is all we have for today. I just want you to keep it real with these real numbers. All right. Good luck with the packet. Dirkus out.